Welcome back to Differential Calculus. In this video, I'm going to talk about approximate area. And I'm going to take us way back to when you first learned about the idea of area in planar geometry. And we're going to look at an idea that you've seen before, I am certain, but it has probably been a very long time since you've thought about. Let me get my head out of the way, and I'll show you what I mean. The definition of area tells us that if we have a rectangular region and we divide that region up into small squares, and I'm going to use the grid size of the graph paper that I write on to define my squares. A little bit of highlighting to make them a little bit easier to see. Most of you probably not an issue, but depending on the brightness of your screen and the size of it, it might be a little bit hard to see each of those individual squares. But then we count up the number of squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 5, 6, 7. And I count that there are 66 such squares the way that I drew this rectangle. And at this point, you are probably questioning why I am bothering with this, because that is something that you learned about in elementary school and haven't thought about since. Because why would you? You can just multiply the length times the width, and you get there. But the interesting question here is what happens if you have a weird shaped region, like this kidney bean looking thing that I just sketched out? Well, you can use the same trick, and you've probably seen this, but it's been a very long time since you thought about it. You can count up all of the squares that are enclosed in this. You can make some judgment calls on the squares that are on the border, and you can get a pretty good approximation of the area. And that absolutely works, but the idea of judgment calls is something that I would like to avoid. Right? Mathematics is all about being strict and rigid in our definitions and having things clearly defined so that if two people look at this, they come up with the exact same value. And so in order to do that, I'm going to introduce two new concepts. The first one is called the lower sum. And for the lower sum, I am going to count only the squares that fall entirely within the region. So this square here is fine. And this square here is perfectly fine. But this square right above, that corner is just outside the region. So even though it is incredibly close and 99% of the square is inside, it's not all there, so it doesn't count. And so just following along and capturing all of the squares that fall entirely inside the region, we can outline the space and get something that looks like this. Again, I probably don't need to line every single square here for most of you, but if you're looking at this on a small screen, that might help it become a little bit more clear what's happening. As you're following along, if you're taking notes, you're not going to come up with the same value I did, and that's okay, right? The numbers aren't important right now. What's important is the process. So the way I've drawn this kidney bean looking thing, I have a certain number of squares that fell inside and a certain number of squares that did not. If you tried to draw a similar shape, you probably didn't get the exact same result, and that's okay. The process is what matters. Counting these up as before, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54. I get that the lower sum of this figure is 54. Now, using the magic of a touchscreen monitor, I am going to go ahead and copy this figure and, as closely as I can manage, get this lined up on the grid the same way as the first version was. That's the real reason that I took the time to trace out all of the grid marks, so that I can move this around and be successful at that. All right, so that was the lower sum. We know that the lower sum underestimates the area. The actual area of the figure has to be larger than the result of the lower sum. Up next, I take it to the other extreme. I am going to count every square. All of the squares that we've already counted still count, and all of the squares that are close will count. So this square that we were talking about as being really close counts, this square that is almost entirely there counts, and this square, which is just barely touching in the bottom corner, that one counts as well. Right, so every square, no matter how little of our shape falls into the square, it will still count. Looks like we'll get an outline that looks something like that. So to save myself some sanity, we've got 54 spots that have already been counted. I'll just start from there. So we've got 55, 56, 57, 58, 59, 60, 1, 2, 3, 4, 5, 6, 7, 8, 9, 70, 1, 2, 3, 4, 5, 6, 7, 8, 9, 80, 1, 2, 3, 4, 5, 6, 7, 8, 9, 90, 1, 2, 3, 4, 5, 6, 7, 8. The upper sum is 98. And that is a huge range, but I know that the actual area of the figure is somewhere between. That feels kind of terrible. I put a lot more work into it than a 5th grader would in a similar project, and I got that the area is somewhere between 54 and 98. That's it? But again, the numbers don't matter. The process is what matters. The size of the grid that I chose was completely arbitrary. I could have chosen a smaller grid. Right? Let's say that these grid marks are 1 centimeter apart. What if I subdivided all of the grid marks by 10 so that the grid marks were 1 millimeter apart? Then instead of getting areas in square centimeters, I'd be getting areas in square millimeters. There's 10 of them in every marking. There's 10 by 10, 100 of them in every one of these squares. So the squares that did count, come back up here so I can actually reach it. The squares that did count, that were on the border, still count. The squares that didn't count, that seemed really close, most of those will count now. The squares that did count over here, that didn't really seem like they should count much at all. Most of that square will not count. And so my lower sum will get larger. My upper sum will get lower. If I subdivide further, it will happen again. My lower sum will get larger, my upper sum will get lower. If I keep doing this often enough, eventually the numbers will meet in the middle, or come close enough to meeting in the middle as to be indistinguishable from nothing happening at all. Mathematically, we call this the squeeze theorem. The squeeze theorem says that for continuous functions, f of x, g of x, and h of x with f of x less than or equal to g of x less than or equal to h of x, if the limit as x approaches c of f of x is equal to the limit as x approaches c of h of x is equal to L, then the limit as x approaches c of g of x equals L as well. This is the tool that we're going to be using here. We have our lower limit, lower sum f of x, which came up with this smaller number, 54 in this case. We have our upper bound, the upper sum 98, which came out at 98 in this place. The area is somewhere in between. And as we divide this up smaller, and we divide it up until we have infinitesimally small pieces, and we divide this up until we have infinitesimally small pieces, those sums will meet in the middle. The limit, as the number of divisions goes to infinity, of the lower sum and the upper sum will be equal. And it has to be that the area of the figure will take on that value at that moment. This is the foundational idea of integral calculus, and it is the foundational idea of geometry. In fact, the definition of geometry, of area in geometry, comes from exactly this argument. As problems for you to try on your own go, this is a little bit challenging, because if I draw a figure here, you're not going to be able to copy it down exactly. So I'm going to actually have to ask you to do this backwards, because it's the only thing that I can really ask of you. Find a sheet of square graph paper. If you already use graph paper for your notes, or you just have it on hand because it's useful, that's easy. If you don't, just go to the internet, go to your favorite search page, and search for printable graph paper. I guarantee you will find something that you can download and print out and use. All right, so find a sheet of graph paper, and I want you to draw an irregular planar figure, something like the kidney bean shape we just looked at. Draw an irregular planar figure so that the lower sum of its area is 23, and the upper sum is at least 35. So the lower sum I am putting an exact value on. The upper sum, you can make it larger if it's easier for you, but it has to be at least 35. All right, so think about the geometry of this. Think about how that's going to work, because really the only thing that you're taking away from this video is the vocabulary of the lower sum and the upper sum. All right? See what you can do with that one, and I'll see you in the next video.